sorry about that. I meant to hit record because I saw my stream had some trouble to reconnect, and I stopped streaming. So here we go again. All right. So the hydroxyl radical then is extraordinarily fast reacting, and it will react with quite a few things. So we can use that if we form it to then go and react with, which can react with hydroxide, OH minus, and form two superoxide radical anions, so two O2 dot minuses and H plus. We could also have a reaction then with ozone and that superoxide to get us a ozone radical species and molecular oxygen, O2. This guy can then react with hydrogen and get us HO3 dot. And from there, we could react, that guy can react, dissociate to give us oxygen, diatomic oxygen, and a hydroxyl radical. So that's a pathway where we can get hydroxyl radicals from ozone reacting with OH minus. So that means if we have basic conditions where OH minus is present in large quantities, we will get hydroxyl radicals because this chain reaction will occur. In total, we can say that for every 3 ozone and 1 hydroxide plus a H plus, so it's kind of like plus a water in a sense, we get 2 hydroxyl radicals and 4 oxygen. So this is a way we are converting from ozone to oxygen with some highly reactive things in between. And this will proceed fast if we have a lot of base present, because we will immediately go to here and form some protons. So that would begin adjusting the pH, but then we're going to consume that proton again and carry on. So that's the deal. We don't really need acidic conditions to start this off. We need the basic conditions. Okay, so basic conditions promote the formation of hydroxyl radicals when we're doing ozonation. So that's a key part of all of this. All right, so this participation of other species, we might call them M for metal or just whatever kind of matter is there. We could consider ozone reacting with M and forming this ozone radical and an M plus. So if we oxidize M, take away an electron, leave it M plus, that would be one reaction. And that would be M as a scavenger to ozone. And if we flip back a page, we would notice that this ozone radical thing could then continue from here to give us hydroxyl radicals potentially. Now, for scavenging reactions, we might have something like methanol, CH3OH, and ozone to give us some transformation. So now we have CH2O, O2, and water. So in this case, we did transform the methanol, but we no longer have any radical or anything reactive left. So it kind of quenched that thing. Even ozone can quench our hydroxyl radicals. If we were intending to use hydroxyl radicals, we have to concern ourselves with the reaction between hydroxyl radicals and ozone. That would give us this HO2 dot and oxygen. And this guy is not as reactive as our hydroxyl radicals, so therefore, if we're converting a bunch this way, we are not, we don't have as much ozone or hydroxide radicals as hydroxyl radicals as we wanted. Okay, so there's many reactions to put together, and it's worth taking a moment to recognize that there are many, many published reaction rate constants for different radicals, namely ozone here, and then other reactive species like hydroxyl radicals and ozone, with different products, or with different potential contaminants. So we have some algal byproducts, like the stuff we care about with harmful algal blooms, the toxin, microcystin LR. Geosmin is like a bad smelling, bad tasting thing that's not really harmful, it just tastes bad. We don't like it in our water, so maybe if we're trying to destroy that. All sorts of pesticides, solvents, fuel additives, DBPs, pharmaceuticals, goes on and on. So we could recognize and study maybe what are these reaction rate constants, how to find them. So there's many published. I'll show another snippet from a really, really large publication in a few minutes that quantifies and kind of tabulates many of them. Okay, if we are targeting the formation of hydroxyl radicals, there's a few ways to do it. We already mentioned the ozone with OH minus, so basic conditions under ozone situation. We can also take hydrogen peroxide, add UV light to photolyze it. We will get hydroxyl radicals that way. We can do semiconductor photocatalysis. I had some slides on that, but didn't get there. These slides I had on the last one didn't get there. And I posted this slide set when I got here. I moved it over so you could see that in case you're following along. So these are now on Moodle, but just like 5 minutes ago. We're not going to talk much more about the photocatalysis, but this is an area of expertise for me. So if you're interested, please let me know. Happy to tell you more. Fenton, I think we mentioned it last time, using iron to catalyze peroxide, essentially lysing into hydroxyl radicals. It's a catalytic reaction that will occur. There are others, some fancy ones, some things that are not quite radical. Single oxygen is not exactly a radical. Even molecular oxygen is kind of a radical, but we don't typically treat it that way. And single oxygen is just a reactive version of oxygen. And there are many things that could quench them, including dissolved organics, inorganic stuff, even, let's say, ozone quenching hydroxyls, and vice versa. So there's a lot that goes on, a lot of pathways, a lot of reactions to consider. Usually when we are targeting the degradation of some organic compound, we might select or consider which type of reaction is going to occur according to which type of radical we're dealing with. I'm not going to go in too much depth, but these include hydrogen abstraction, OH addition, redox reactions in some cases. Obviously, we're doing typically highly oxidizing systems. There is some research going on lately about advanced reduction processes. Of course, you'd have to remove all the oxygen from the water so that it's no longer an oxidizing environment. So that might be useful in some special scenarios, and that would correspond to its own redox and perhaps different types of organic chemistry involved. But you can imagine a pesticide might look a little different than a fuel additive, and the type of approach you'd use to transform it, maybe a different radical works better than the others, which is kind of why we were concerning ourselves with the different rate constants, right? That likely depends on the affinity for a particular type of reaction. Okay, here's the massive text published in 1988. This is Buxton et al. It's a review paper that, and probably they provided some of the data themselves. But if you ever need any information about hydroxyl radicals or oxygen radicals or H radicals reacting with some chemical that was known by 1988, this is your go-to. It's a really long publication. This is reaction 858. I think there's something like 1,000 pages worth of tabulated data. It's really impressive. And they're kind of tabulating all these second order rate constants, giving some notes about the condition and a reference cited for it. One note here is, considering all of that, we often run into what's called a diffusion limited rate. This would refer to the situation where your radical is reacting so quickly that the effective rate at which the reaction proceeds is actually just simply limited by how quickly they diffuse to meet each other, the radical with whatever else it's reacting with. And this would give us essentially a lifetime of that solute, whatever's reacting, of about 10 to the minus 7 seconds. so 100 nanoseconds, if you have 1 millimolar of that solute. So if you have less of it, maybe less, potentially a little longer. If you have more of it, also might depend on what it's reacting with, but this is just kind of a general rule of thumb. Things don't last very long if they're reacting that fast, even if you have a lot of it. Okay, this brings us to an example which will be helpful. It's a little call out here for problem 10.7 in your homework. I think it was 10.7. So take a look here for that, and we'll discuss this a bit. I began working up an Excel sheet. I didn't quite have time to finish it before class, but I'll show you my building towards an Excel sheet to solve this problem, and you can kind of get some idea of how you might go about that for, might have been 10.3 and 10.7 are kind of similar for some of the homework problems. Okay, but let's take a look at this example real quick. 10-14 says relevant chemical reactions for the oxidation of atrazine, abbreviating as AT, by ozone, and the associated second order rate constants are given later. The first reaction is the direct oxidation of atrazine by ozone. The second and third describe the creation of hydroxyl radicals from ozone. And the last describes the oxidation of atrazine by the hydroxyl radical. So we have ozone destroying atrazine, some reactions forming hydroxyl radicals, and then hydroxyl radicals also destroying atrazine. Okay, so we have a lot going on, 4 reactions. We kind of talked a little bit about these before, and for each one of these we're given some rate constant. And this is, if you look at it, it's per molar per second, so that's going to be second order rate constants, meaning it's going to depend to the power of 2 on solutes. Okay, that's, in each of these cases it's actually going to be moles per liter of ozone and moles per liter of atrazine, right? It'll be dependent on both of those pieces. Okay, so then the problem goes on and says determine the atrazine concentration as a function of time over a 10-minute period in a batch reactor at pH 6 under the following circumstances. Now, one thing to note is we're at pH 6, and even though we are potentially consuming some hydroxide, some OH minus, which would change the pH, there's probably either buffer to keep it there, or we're going to make an assumption that part of one of these reactions is counterbalancing that, or it's such an insignificant amount that we're not changing the pH. We're just told that it's pH 6. Okay, so we're going to keep the pH constant and not worry about that part. Okay, so the problem says we want initial atrazine of 10 nanomolars with 50 micromolar of ozone to start, and the oxidation is going to occur only by direct reaction with ozone. So the only way our atrazine is changing is reaction 1. That doesn't mean the other reactions are not happening. So what we might take a look at is the only thing that changes atrazine is this one. However, something else changes ozone. And we didn't mention anything about that. So we're going to have to account for the fact that ozone is reacting with OH minus, and it's reacting with this product that OH minus makes. So in that sense, we will need to account for the fact that this is our primary reaction changing atrazine. So the delta atrazine concentration, delta time, is going to be equal to this reaction occurring. But we also have to account, when we do that, for the ozone, which that ozone's concentration is also changing. So it's going to be a system of equations that we're solving simultaneously, and we're going to leverage Excel to do this in a stepwise manner. Okay, I'm just going to briefly mention the 2, 3, and 4 here. We're going to do the same conditions, but with the hydroxyl radicals added for 2. And for number 3, we're going to change the initial ozone concentration. And number 4, instead of that, we're going to change the initial atrazine concentration, just to kind of see how all those pieces fall into place. So the solution says, we talked a little bit about it in chapter 3, or the book did at least. The mass balance on any chemical I in a batch reactor has the form dc dt equals the sum of the rates. Okay? We're changing ozone or anything, atrazine, as a function of the rates at which that is reacting. So from there, we can, and the summation is overall reactions occurring in the reactor. Apply this idea for the to the 4 chemicals of interest in the given system. The chemicals of interest would be anything on the left side here, right? We have ozone, atrazine, OH minus, but we already said that's not of interest because we're going to keep that constant. Already said ozone. Then we have this HO2 minus and hydroxyl radicals. So that gives us our 4 there that we're interested in. We obtain rate expressions. We'll take a look at in a moment, but we can essentially, even before we even look at the rest of the solutions, we can say, well, we need d ozone dt, we need d atrazine dt, and we can put all this in molar units would be good. Since our rate constants are all molar, we would need the d hydroxyl radicals dt and this HO2 minus, which I forget the name of this one, dt. So we need each of those, some function of them, in order to solve the problem, because all these reactants over here is what our solution is going to depend on. Okay, so for case 1, the only direct oxidation of atrazine, we're really only going to apply this one to the atrazine concentration over time. However, we do need to calculate the other pieces because they're taking away some ozone. So what we're going to do is calculate in step 1 the atrazine that is destroyed according to this reaction based on how much ozone starts with. So for the first second, let's say, we could do 0.1 second at a time, we could do a second, we could do 10 seconds. We're going to do 10 minutes total. So we're going to do the first step with the initial conditions. And we have the rate constants, we have the initial concentrations, and this is our only reaction that's changing atrazine. So step 1 is fine. We encounter that and we calculate it. Then we move on, and step 2, now we also have to calculate how our ozone changed. It changed a little bit because of the reaction with atrazine, but also changed a bit upon reaction with hydroxyl radicals. So as we form more hydroxyl radicals, the HO2 minus, and as it continues to react with the OH minus to form that, we will have less and less of it. Okay? Does that make sense? So when we do all that, if we write out these equations, ozone is changing as a function of the reaction of ozone and atrazine. That was the K1. It's also changing as a function of OH minus and the ozone. Fortunately, this guy is constant, right? So that's 10 to the minus 8 because we are at pH 6. And then it's also changing with K3, that reaction of ozone with the HO2 minus. So every step in time that we take, ozone will change according to those pieces. The next piece would be the atrazine. So we don't have to order it in this way, but this is the one that we're going to actually plot when we get there, is how is atrazine changing? And in the case of part 1, it's only changing according to the ozone. And in part 1, we are neglecting this piece, right? That was part 1, was to say that's not there. We'll say for 1, ignore K4. we'll say ignore hydroxyl, and that would be as if we set K4 to 0. Okay, whatever we want to do to cancel that. All right, and 2 would just simply include it. 3 and 4 are simply giving us different starting concentrations for ozone and atrazine. Okay, so we can write up each of these rates. So the rate of change of hydroxyl radicals would be in reaction with this HO2 minus and with atrazine. And we have the HO2 minus changing, being produced according to this ozone and OH minus. And excuse me, I said this wrong earlier. This one's a production, right? We're producing with ozone and the HO2 minus and reducing it or removing it with the reaction with atrazine. And here we have ozone and hydroxide forming this guy and ozone and this guy removing it. So if we were to work on this in Excel, I think it probably ought to look something a little bit like this. We have the rate constants written out. A pH at 6, that gives us a particular H plus concentration, but what's more important is our OH minus, 10 to the minus 8. For our 4 cases, I have written each of the initial conditions and some notes. So the difference between 1 and 2 is simply that we are using the normal K4, whereas in case 1, I just went ahead and set K4 to 0. We have all our reactions listed out there, and all that. So all that there as a reference. And then part 3 and 4 simply have the different initial conditions for ozone or atrazine. All right, otherwise, here are the initial conditions, or the rate constants and the initial conditions up here. Then what we would do is come down and put in our initial conditions for, let's say, atrazine at time 0. In case 1 would be what was given, right? We start with the initial conditions at time 0 of what it was given. So we can go ahead and fill that in for each column here, each species in each column. And what I did is I went ahead and took 5-second steps. This is arbitrary, but it gives us plenty of steps between within the first 10 minutes. So then to calculate ozone, again, kind of starting with the first set of reactions here. You don't have to start there, but I went ahead and started there. We can calculate the concentration of ozone at the next step. So the first step we start at time 0 is the initial condition. The next step would be we would take the initial concentration and then add whatever change happens within 5 seconds. So we take the time multiplied by these rate components, right? And so over 5 seconds, we expect some amount of change. We have these rate constants as a function of per time. And we would include, so this is the time step, multiplied by the sum of each of those rate components. This is subtracting, if I did it right, this is subtracting from all of them, and we will have a little bit less ozone. And if we repeat this every time, we will get a column where we track the ozone concentration for the 10 minutes. Maybe it doesn't change much. Maybe it's much higher concentration than other stuff, so a small change, especially at the initial time where there's no HO2 minus and no ozone to react with, looks to me like not much happened, okay? This might be a rounding error, so if I were to, we see there was actually some change, right? If I put that, the decimal place way out there. Okay, so good to know to check that it looks to me like I did my equation correctly, because I was expecting a tiny change, but not a huge one, right? Okay. From there, we would do the same type of process for each species that might be changing and ultimately get an atrazine profile for case 1 as a function of time. This is a way to stepwise, or a numerical solution for a system of differential equations, right? That's kind of the deal. So if we do that, we should be able to get something like this plot. And like I said, I didn't quite have enough time to generate the entire thing, but this is what I would be aiming at to make sure I can replicate it, right? To see if I can get that atrazine concentration. We see case 4 has a smaller starting concentration. That's why it starts here. Otherwise, they're all starting at 10 and decreasing from there. As we might expect, case 1 has the slowest decay of atrazine because it ignores the hydroxyl contribution. And then 2 and 3, we're changing the amount of ozone. So the one that has more ozone obviously should have a faster decay of atrazine. And the last step, we start with much less atrazine, and that reaction takes us to approximately 0 atrazine remaining rather quickly. Okay, does that make enough sense? Yeah. Yes, yeah, I can do that. And I'll see if I can add a little bit to it and perhaps make it work if I can do so in a short amount of time today. Really what we're doing is every time step we are calculating a new concentration of ozone, a new concentration of atrazine, a new concentration of OH2 minus, and a new concentration of hydroxyl radical according to these equations. Yeah. So we're going to assume that the hydroxyl radical initial should be 0 because we've not done anything to form it yet. And the HO2 minus, or HO2 minus initial should also be 0. So that's what I did in my Excel file to say what we're starting with, well, no fancy reactions have happened, so hopefully those would be 0, or that would be a fine assumption to make. Another thing we could consider here is essentially what I'm doing by doing it numerically is if we take a small enough step, we are doing delta, the change in concentration per delta time, and equals all those reactions, and then we are multiplying both sides by delta t. So we get a delta concentration equal to the stuff on the right side, and we can take that delta and add it to the next line of our calculation. So if I say this as the sum of the rates, then we could say of x, delta x would be equal to delta t times that sum. Okay, something like that. Yeah, you could certainly use MATLAB for this. That would be a good use of MATLAB. You could potentially even do, I think you could do a system of ordinary differential equations and I think MATLAB might be able to solve it analytically in addition to numerically, but you could certainly do numerically with MATLAB. And let me know if you do. I'd be happy to see that. All right. So, quick note on sources and sinks. Basically, another way to visualize where our radicals going and what is taking them away from our systems. We could have schematics like these to show, okay, we are generating some hydroxyl radicals for some advanced oxidation product or process. And so we have some pool of hydroxyl radicals. Then what happens if we go through some chain reaction? So for methanol, we react here, we go through a few steps, and ultimately we are left with an H plus and a superoxide radical anion. That, depending on which AOP we're in, could actually convert back up into a hydroxyl radical. So in some cases, given that a radical is essentially defined as an unpaired electron, if we never give it a situation where it is paired back up, we may be able to recycle radicals with some input or with some catalytic action. So sometimes we end up with something that's reactive and ultimately comes back to the pool of hydroxyl radicals. We can see that same type of thing with the benzene ring here. However, in the case here, this is tert-butanol, I think, we have a case where we end up with no radicals produced. This guy here is, I think, just pretty stable and will eventually decay, or let's see, it kind of has trapped that radical and it's not going to be particularly reactive from there. Okay, and we'll look at a couple of these just real briefly, just to kind of highlight a few pieces like that. All right, just a quick bit about peroxide, UV and peroxide. We know that hydrogen peroxide absorbs with a spectra that looks like this if we had 3 to 7% solution of hydrogen peroxide. And so that means we can use wavelengths kind of in this range with UV light, which corresponds pretty well with our mercury lamps, which tend to emit strongly right here. So if we use a strong mercury lamp, like low pressure mercury lamp, we're absorbing a decent amount of that energy. Perhaps we could shift that lower. Maybe the fancy 222s might be a little better. Those are kind of a new thing lately. They don't go too far through water, so that might be a problem just in and of itself. But at any rate, what we can do is photolize using that UV, the peroxide, get 2 hydroxyl radicals for every 1 peroxide. And that would be getting us quite some good reactions. We also have to concern ourselves with the fact that if we have particular pH, we will have an equilibrium of peroxide with HO2 minus. And that one has a stronger UV absorbance and can also photolize, so that's actually kind of a better thing. So if it's a bit basic, that's a little better because we have a little more HO2 minus. Okay, we could talk more about that with quantum yield, things like that. And another thing we can recognize, we talked about the superoxide radical anion a couple minutes ago. If we get a couple of those together, we can essentially form some of this, some of the HO2 minus, which can then get us to peroxide and oxygen. Again, a couple of sources and sinks for a peroxide type of system. We can look at methanol going through that same type of process. We could potentially get back to peroxide and therefore potentially back through our system into hydroxyls. However, if a hydroxyl radical reacts with bicarbonate, which is very common in our natural waters, right? If there's any carbon dioxide around, there's going to be at least some bicarbonate if we're near neutral. That is reactive with our hydroxyl radicals and will just take them away altogether. So it quenches them. We have no more OH dot remaining. So that's a competing reaction with whatever we're trying to oxidize. Okay, there's more we could look at, but that's the premise there. Okay, this one feels a little bit out of order perhaps, but kind of in the same thinking of what is reacting where. Taking a look at ozone in the context of hydroxide that can form hydroxyl radicals, we have some pH dependence. And if we look, this left plot is looking at the fraction of oxidation mediated by our hydroxyls. So this is what portion was driven by OH dot versus the ratio of concentration of OH radicals to ozone. So this would be on the x-axis, we have OH dot divided by ozone. So the more hydroxyl radicals we have, the further right we go, and the more accomplished by hydroxyl radicals, the higher we go. So if we're really, really low, our hydroxyl radicals are really not doing much, even if we have a lot of them. That's the case. So we can see a clear difference. MTBE, methyl terbutyl ethylene or something like that. This is an additive to a fuel agent to stabilize our gasoline and stuff. Reacts very quickly with our hydroxyl radicals. Hydroxyl radicals do almost everything compared to ozone. Whereas these guys down here, whatever SMZ is, CMZP, whatever those are, it's almost all ozone if it's going to go away, even if we have tons and tons of hydroxyls. So that's kind of what that plot's showing. That can vary based on their reactivity. Now, the plots on the right, coming back to the concept, the topic of atrazine, we have three different pHs. No, two different pHs, sorry. Two different pHs, 20 micromolar of ozone versus atrazine concentration. Just two different scales for the x-axis. So we see that pH 8 causes a rapid drop in atrazine concentration, and pH 6 is much slower. And that would tell us that, hey, ozone's going to react with the hydroxide, therefore it's going to create hydroxyl radicals, and we can interpret this to say atrazine reacts very quickly with hydroxyl radicals compared to with ozone, right? Could do some calculation like that, or at least some assessment to say, you know, I could give you this on an exam, right? Which is this more sensitive to hydroxyl radicals or ozone, right? Based on that, what do you expect, right? It would be, we would see that, hydroxyl radicals are very important because we expect more of those with ozone under those conditions. Okay, almost done with AOP stuff. So another thing we can do is react ozone with UV light. This will give us a few reactions, and this is actually occurring all the time up in the upper atmosphere, giving us nice shielding from ultraviolet light. If we take a look at the absorption, the UV absorption for ozone and oxygen, we'll see that oxygen itself absorbs almost all light, pretty much practically all, up to something like 175 nanometers. So that's pretty far into the UV. Ozone absorbs very strongly, even up into the UVB range, where 300 nanometers to kind of 320 or so, even there it's absorbing, and it also absorbs pretty strongly right where we have our typical mercury emissions, right, for a mercury lamp. So ozone absorbs UV light quite strongly and can then photolize into oxygen and this oxygen radical, the O dot radical. Well, water can then react with that oxygen radical to give us hydrogen peroxide. That would be a redox reaction because the oxidation state of our oxygen is changing from a 2- to a 1-, right? So that'll give us peroxide. Ozone, like we said earlier, can also react with HO2-, which is the conjugate base of that, and give us this oxygen radical and this HO2 dot radical. Okay, so all these pieces give us some radicals to potentially work with if we use UV and ozone. So that's another AOP potential. These single oxygen atom radicals might be able to be useful in reacting with stuff, or maybe it's just going to give us more peroxide, which can give us more hydroxyls and so on. There is another thing that can form from this single, and I was going to, I need to change this. I was going to highlight that this is different. The single oxygen radical, I'm erasing that T because we call this guy singlet oxygen because of the singlet state of an electron, but it's O2. This is also reactive. Maybe that's not technically wrong, but it's misleading in my opinion. But we can get this guy, singlet oxygen, from ozone forming this single oxygen that could react with oxygen, O2, in our ground state, and this when we form this, we can form these guys, and some of these are the single oxygen. This is the particularly reactive one that we could care about. Anyway, don't worry too much about all that. My point is just that we get all sorts of radicals, and if you're interested in this stuff, we can talk more about it. It also means if you're worried about the ozone layer, if you ever think of it, it's actually catalytically produced when ozone absorbs strong UV. So there's always going to be a source of new ozone in our upper atmosphere. The trouble is if we have something catalytically removing it with these radical chain reactions consuming it. This is why particular compounds are not so great to have in the upper atmosphere, and why once we let them eventually come out of the atmosphere, we will have ozone again. It's just kind of how it works. We also don't want ozone down in the lower atmosphere. Okay, more sources and sinks, same kind of deal. We could look all sorts of places and find different things. Again, highlighting that hydroxyl radicals are kind of our central focus. Bicarbonate is a definite problem for that. And given different circumstances, maybe we care about our ozone. Where is that coming from? Are we recharging that? And so on. Not going to go any deeper there. Okay. So a couple things for homework 3. In problem, in addition to the example problem that we took a look at, I hope will be helpful in the Excel file, you also need to look back at table 10.3 for problem 10.3. I don't know if they did that on purpose, but you'll find that the book is providing some information on cyanide that you're going to kind of need. I think the problem gives you some expression and tells you that one or the other of these reactions is the important one. Well, we could even look, right? KHA is 10 to the minus 5, where Ka minus is 8 times 10 to the 3. So I can already tell you this one's the important one. And you're given that by means of the book giving you that, but the problem doesn't remind you of that. So that would be a case where you'd kind of be given that data, so you don't actually need to find it from the problem. The question I received was with relevance to how you might go about finding a K given a CSTR, which that problem has. So just a quick reminder, this is not what you need to be doing for that problem because you're given the K. But if we imagined we were given, let's say, a half-life, so half-life in a CSTR context, can we work with that? Well, when we've done half-lives in the past, we said, natural log of 1 over 2. This is basically the natural log of C over C naught equals, for a first order, negative KT, right? And then you can solve for T, where this is the half-life, and solve for K that way. We'll just leave it like that. In a CSTR case, you might be able to say something like, if we find C over C naught, again, let's say first order decay, our mass balance would come out to be 1 over 1 plus tau k. In which case, we could say 1/2 is equal to 1 over 1 plus, if we're using that half-life, we might be able to just put in a half-life time. We'd have to be given some specific information, and normally to say that, you know, maybe a particular residence time cuts the so I'll say this, yeah, well, I'll just leave it as t1/2. But it would have to be very specific to say, in this CSTR, at this residence time, was able to reduce it by 50%, right? Then you could set up something like that and solve for a k. Like that's possible, but again, that's not what the problem is asking for, because the problem does think you remembered that table, essentially, or looked it up or something. Okay. Yeah.
Could you set up the Ka equation for this? Because I'm not understanding what it means. I'm not used to seeing
Yeah,
like 3 different compounds listed.
Yeah, so this problem in particular is, the challenge of it is recognizing that for CN, we have 3 different species. We have CN, I guess, sorry, not 3. We're showing 3 different rate constants here, and I'll explain why. We have CN minus, cyanide, and we have HCN. We could also say we have a total cyanide as the sum of those 2. Oops, HCN. So what this table is showing us is, first of all, it's giving us our pKa, so we know the ratio, given some pH, between HCN and CN minus. Then we have a rate constant for the reaction of HCN. So in this column, we can treat this as HCN. And in this column, we can treat this as CN minus reactions. And then they also give us a rate constant for the total, if you just had the total cyanide in solution as a value, but at a specific pH. So it already factored in all your pKa stuff for pH 8 for this third column. So this third column shows you that it's possible to make an average K, but it didn't do it for you for the pH that the problem uses. And that one's not really going to be relevant for your problem because you're at a different pH. But it might also kind of show you that you might need to do something similar. For that problem, you're going to have to apply this value to only the CN minus. But to get CN minus, you're going to have to work with the equilibrium, right? So Ka, sorry, let me make that a little clearer because I'm talking about this Ka now. So I'm going to say uppercase K, and they're doing lowercase a. Yeah, we'll do that. Ka is 10 to the minus 9.21. And this is going to be equal to the products over the reactants. The products of HCN dissociating should be H plus and CN minus, divided by HCN. We could also say the total cyanide, as I mentioned, would be, I already showed that. So there's 2 equations there that we can use to relate our cyanide. And then in our mass balance for that problem, we're going to have to account for how much of the total is in this form and multiply that by our rate constant for A minus. Does that make a little more sense?
I still don't know what the products and reactants are for the Ka minus reaction.
Okay, so the as with most equilibrium reactions, I'm just going to carve out a space. We're looking at HCN dissociating and losing a proton. So this is going to be in equilibrium with H plus and Cn minus. So that would be just like water or just like HOCl dissociating and losing a proton. So you've seen things like this quite a bit. Does that answer your question?
Where does the chlorine dioxide factor?
Okay, so good question. So the chlorine dioxide, I think the problem is just simply saying we have ClO2 reacting with Cn minus, and we're ignoring any reaction with HCN. So it's the chlorine dioxide is reacting with this guy and converting Cn minus, right? So that's going to be the reaction, if I recall correctly, you need to balance that equation first and set up the mass balance from there. Maybe not, something like that.
Okay, so there's oxidation of HCN and then there's oxidation of Cn minus occurring simultaneously. So just that HCN is the original.
Exactly. So technically speaking, they're both oxidizing, but one is much faster and much more important. Okay. Yeah. We'll talk about that Thursday. I wasn't planning on it, but if you guys manipulate me again, maybe.
Yeah, definitely being able to take my time with each question. I wasn't rushing through it.
I'll make it easy if it's in person. We'll say that.
You don't want to grade me.
Unfortunately, I have to grade 95 exams already, so what's 15 more? All right. Okay, we'll have more of a debate on that on Thursday. Any other questions about this? We'll also, of course, talk about the homework Thursday. And that gives us right about 20 minutes for me to give you the real short version of the Flint water crisis. So here we go. We'll pause for a timely sip of water. All right. So in 2014, it just so happens a lot of things happened. I ended up moving to Lansing. And, well, let's see. I did a lot that year. Finished grad school, got married, engaged, then married, and moved to Lansing because my ex had a job at the Michigan Department of Health. And it was kind of a 2-year internship type of thing. She was in epidemiology, so some of what I have today is coming from her experience and kind of sharing a bit of that. Some of it's my own experience or just hearing about stuff. I ended up working at Michigan Department of Environmental Quality for half a year in 2015. Thankfully, I was not in the water, like the drinking water. I was in kind of the wastewater permitting because could have been in some hot water if I happened to be in drinking water, which is kind of what I was aiming for because that was a little more my expertise at the time. Anyway, I'm there, Flint is here, and the Flint water crisis happened. So just a bit of geography. Detroit is here, that'll become important. They were sending water up to Flint. If we zoomed in on Flint, we'll see the Flint River is winding its way through somewhere like that. And the city of Flint began taking water from there. They had originally and again, I'll talk about this in a minute, been planning to begin taking water from a pipeline that would come down from here. So what exactly happened? What is it? What is the water crisis, Flint water crisis? Well, the primary big thing is lead in the water. Lead is a neurotoxin. It's not good for anybody. It's especially bad for children, and children had lead poisoning because of this thing. There was also, in addition to that atrocity, there was a Legionnaire's disease outbreak, and there were some issues with the Flint treatment plant where there was coliform counts that were too high, triggering some boil water advisories. And when they tried to fix it by overchlorinating, they formed disinfection byproducts and got dinged on that too. And there's a couple of great papers from Mark Edwards' group at Virginia Tech, and he has an entire lecture on this. I think I've got those materials posted, or I'd be happy to post them if you're interested in it, if they're not up there already. I have other extended lectures of this sort, but you're getting the quick version. All right, so timeline. History tells us that there used to be a lot of auto industry in Michigan. That was very important. Even before that, we had lead pipes in the ground because the Latin root for plumber, PB, is where we get PB. Plumber, that's our abbreviation for PB, lead on our periodic table. That's coming from Latin. Just so happens that lead is workable. It retains water. We can make pipes out of it. We can make joints out of it. Very easy to work with, pliable, yada, yada. Cheap, pretty abundant. And so it used to be pretty common to have lead pipes, put them in the ground, and forget about them. That's just the way of it. And in fact, that's actually not the worst thing in the world if you prevent the lead from corroding. It's actually usually quite safe, all things considered, given how bad lead is, surprisingly safe, that it's pretty much okay. I think there's been some controversy over the years about pewter dishes, which was a lead dishes. If you use pewter and then use some acidic, like tomato juice or something, that can give you some big problems. All right, so then there's the auto industry, 1930s through 60s. It booms, then it busts. That means there's localized economic depression in and around Flint and other areas in Michigan in particular, but all up in the Rust Belt. That's particularly relevant for Michigan because then in the early 2000s, the state government decided to stop a revenue sharing program where revenue from, let's say, Grand Rapids was being shared with Flint or Detroit or different things like that, spreading the city tax revenue to places that were really hard hit by the economic collapse. There's a lot of debate you could have about what's right, what's wrong. I'm not really here to comment on either of those, but it is understandable to me that you might want to support a place that has collapsed economically, but also to stop supporting them eventually because you're taking money from some people and giving it to other people, and that's not necessarily ethical either. So in the one case, it might be philanthropic. In the one case, it might be unethical. Anyway, that leads us to a situation where the state begins appointing emergency managers to manage the finances of municipalities like Flint. So in 2011, I think the first one was appointed. These, as we'll see, are a terrible situation because this appointee is not necessarily equipped with decision-making skills for anything except maybe a budget, right? And it could just be the governor's friend, could be, who knows, right? Just somebody. And some of these cycled back through. It was a one-year appointment at a time. They weren't from Flint. They weren't representing Flint. They were just there to manage Flint's money because they were going bankrupt. Kind of understandable, but also kind of terrible. So in 2013, the emergency manager of the year decides to switch water sources from the Detroit Water and Sewerage Board in hopes to save something like $5 million over a few years. I think maybe we'll just call it 5 years. I'm not sure if that's exact, but it's something along those lines. Save some money over the course of the next few years of the contract was the idea. Well, Detroit's a bit fussy about that, or their water and sewage board, and gives them a 1-year termination notice. Say, oh, okay, if you're making these plans, well, it would have been nice if you had consulted with us, but get out of here. And those were the plans to take water from the other location. Flint realizes that's not enough time to finish the renovations they had planned for the new water supply. And so they have to make backup plans. Essentially what they do, let me get my own camera out of the way a little bit. What they do is they switch to the Flint River. Now, Flint did have a water treatment plant, but it was small. It was really only designed to re-up the water quality from the Detroit, what they were receiving from Detroit, and send it out. So it was really not up to the task, and the Flint River happens to be more corrosive than the supply that Detroit was giving them from Lake Huron or whichever, forget where exactly. And that is the big issue. As soon as this happened, and they did not add corrosion control to the water as they should have, that's the big issue. So that's the start of our Flint water crisis in April 2014. Immediately, Flint residents are complaining about it. It's immediately obvious to them that there are problems. By August that year, there are high coliforms. There's more bacteria in the rivers and stuff. It only really gets warm up there by like July and August. It's like kind of March weather here. It was funny hearing them complain about hot and humid. I'm like, guys, it's 88 degrees and a little bit humid. And this was before I came here. I was just me coming from Georgia. Anyway, there was boil water advisories. There was high THM counts. That's the trihalomethane disinfection byproducts. When they upped the chlorine to account for that, boom, they had disinfection byproducts. It was not set up properly. It was not designed. It was approved when it should not have been approved. Some engineer somewhere either made a terrible mistake in approving it, or perhaps was forced into it. I don't know. And they missed the net absolute need for adding essentially phosphate does it. That orthophosphate is a great corrosion inhibitor. So corrosion control is what they needed and didn't have. In August 2014, the city officials were literally telling their residents, the water is fine, drink it, it's safe. But they were getting bottled water for their own office, like trucks of bottled water coming to the city government office so that they could have nice water to drink. So they weren't even drinking it. The hypocrisy was insane. By December 2014, Flint had already spent $4 million on water treatment plant upgrades. It's probably most, if not all, of what they were planning to save over several more years. Also pretty terrible. By January, the Detroit Water and Sewerage Board offers to reconnect and to waive the fees. And this sounds like, okay, cool, I'll waive $100. No, this is going to be the fees, including all the construction costs, including the planning, the engineering drawings that are required to set up the excavation, do all of that, right? This is big money. So if you might point a finger at Detroit for being kind of fussy with them and canceling a little earlier than they could have or should have, well, at least they're making a pretty good faith offer here by this point, because they recognize Flint's in trouble. Of course, there's an emergency manager that's thinks he or she is smarter than everybody and rejects that. City Council votes unanimously to reconnect, but the emergency manager, still on a power trip, rejects it. So the City Council is trying to get safe water. I mean, at this point, nobody knows for sure that the water is bad. When it's coming out of the treatment plant, aside from the lack of corrosion control, which is not something that's, I guess, necessarily monitored directly, it's maybe assumed that it's added, the water looks fine, right? For the most part, aside from when they were getting the disinfection byproducts and the high coliforms, aside from all that, it was fine and safe to drink out of the treatment plant. And then there were issues with the lead and copper rule not catching the lead in the water. By mid-2015, there was a pediatrician that recognized that her children's blood samples were way too high in lead and was very concerned. This was in Flint or nearby. She contacts Mark Edwards, who had worked on similar issues, I think in DC, perhaps elsewhere. And that kind of kicks off the first time where we recognize there's lead in the water. That's like the identification of the Flint water crisis. By October 2015, Flint does switch back to the Detroit Water and Sewerage Board, division, whatever it is. That means corrosion control is coming back. Essentially, this is the end of the Flint water crisis as we know it in terms of the lead. Because as soon as we've got corrosion-controlled water, we are no longer etching away at our pipes, and we are allowing mineral deposition on the pipes, stabilizing it. There might be a few particles kicked off from all the damage that was done, all the corrosion that was done, but even with lead pipes in the systems remaining, the problem goes away very quickly once we adjust the chemistry properly. So that is, in a sense, the end of the Flint lead crisis. Of course, in the years since, they've made a big effort to replace all the lead pipes. But January 2016, the governor finally admits that there's been a Legionnaire's disease outbreak going on for the past 2 years, probably associated in part with the water. And eventually, in February 2017, the CDC finally links that Legionnaire's disease outbreak. That was a bunch of drama as well. The legal outfall has continued. For a while, there was governor and officials charged with felonies, misdemeanors, involuntary manslaughter related to there's some people that died from Legionnaire's disease, usually the very sick or elderly who were already on their deathbed. Legionnaire's disease is a difficult pneumonia, so it's potentially very harmful for people, and so some deaths were attributed to that. In 2022, some of this was overturned because it was apparently a one-person grand jury that was making these indictments. So that was overturned, saying that's not quite kosher. So I think some of the charges were still pursued or whatnot. I'm actually not exactly sure, but some of it was perhaps overcalibrated and walked back. I don't know. 2023, the Genesee County Court approves Flint water settlement. Later that year, Michigan judge drops these felony charges, probably according to this. Oops, sorry, I just hit the wrong button. Okay. And also in 2023, there was a few deadlines missed, but it was only missed by a few months. So I think they got that kind of cleared away. And finally, this year, the last lead pipe was removed. In my opinion, the lead pipe removal, while not strictly necessary, was probably a very good thing for the peace of mind for everybody involved. So it's probably the right thing, even if corrosion control was truly the answer that we usually rely on. It's actually very difficult to find which pipes are lead when you don't have the blueprints for every single house and every single premise and all that. So that was a really, really big task. Took a lot of effort, a lot of money to do all that. So no small investment, and I'm not sure it would be recommended for every location to remove all the lead pipes all at once. But there have been some revisions to the lead and copper rule, which do include ongoing updates to try to remove and to work towards removing all of lead pipes. Okay, big picture here. There's big failures in corrosion control, inadequate treatment capacity. You can see a couple pictures from one of the Mark Edwards papers here. This is what the water looked like under Flint water. And a couple years later, so this was October 2015, and by March 2016, it looked more like that, right? That change. So pretty clear that residents recognized there was a problem. Pretty obvious. Excessive chlorination. Chlorine is also an oxidant, by the way, so it's corrosive. Corrosive water supply, many vacant homes. That's kind of just part of the history. And then when you have a lot of vacant homes or a lot of vacancy, there can be long periods of time where water is just sitting there. That is probably why the Legionnaire's disease stuff was an issue. There's also a big issue that the lead and copper rule, which is supposed to catch stuff like this, didn't catch it. And there was some controversy with that. How are they doing the statistical analysis for which taps they sample in the distribution system? What data points do they discard as outliers? There were some rules, and I think they were followed, but there was some controversy of, was this manipulated? Was this not followed according to proper etiquette? So these rules got some updates over the years since to really make sure that that's not going to happen again. All right, so the lead and copper rules, few little things here. Just going to highlight, it originally had replaced 3% of lead-containing pipes per year, but it had some exemptions. So now it's revised to, it was 7, but there was exemptions. And now it's 3%, but no exemptions. So no matter what, municipalities with lead pipes will be replacing them over time. There's some other improvements with a deadline of October last year, more communication, stuff like that. I'll let you look further if you are interested further. All right, I've got 4 minutes. Legionnaire's disease. It's not really spread person to person. It's also called Pontiac fever. It's usually spread by cooling towers that have a bunch of bacteria in it, or showers. It's also, so it's common throughout the world. It's fairly prevalent in Michigan, just naturally occurring there. When you get sick with something that is reportable, it's supposed to go and into a surveillance system. There was an issue where there were cases, the health department was supposed to catch the DNA samples and report it, but they reported it and refused to do the DNA sampling because they were fussy with the state. They actually even tried to go straight to CDC, which would have been like not even here, but further. And they wanted to skip because they were not being professional. Some stories about that. So things like Legionnaire's disease are reportable and should go through that category. Something like the flu is not reportable, which is why we don't have cold hard numbers of flu cases. Things like COVID, we tried to make reportable, but turns out that's not like the flu. That's not very possible. And so you've probably learned some stuff about all of this in the first place with how this would work, how you get it there, the role of asymptomatic. You're not catching all of the reports. Things like Legionnaire's disease, if you're hospitalized and they find it, it's pretty common to report it. And so historically, there are some cases every year. And then you see in 2014, right around May, you remember that so this is a summer type of disease because the bacteria thrives more in the summer. But right around April was the Flint water change, the crisis. And boom, big spike in cases. And then the following year, same type of thing. I think I've got data right here. So there's a big question, and these are epi curves, so cases over time. And it turns out there's a big controversy because a lot of this was associated with a hospital that tried not to be named for a while. Ultimately, I think it came out that McLaren Hospital was probably largely at fault, and they weren't really cleaning their system as well as they should have, but that was probably in part triggered by the new water supply. The new water supply introducing some Legionnaire's disease, so the hospital was likely infecting their patients that were at the hospital for other treatment, and that was a big problem. So you see here, they did hyperchlorination here, and then they did superheating with hyperchlorination, and then finally they added some residual monochloramine to have a long-lasting disinfectant stay in there for a longer time, cleaning out the system much better. And these are percentage of samples that had positive concentrations for bacteria. Ultimately, there was some question about, are we blaming the water or the hospital? And this kind of data is a little tough because you don't always know what and even the person doesn't always know which water supply they've been on, right? So there was people from the city of Flint water, some number of them, 47% of the data in 2015 for the people that got sick, 7% on a different system, 9% on other systems, 16% private, 22% don't know. So it's a little bit difficult, but it's likely that it had something to do with Flint water. And then there was the curve of, well, were you exposed to this hospital? A large portion of them were. Okay, so at least a good portion of this outbreak did correspond to that hospital. The crazy thing is, my ex was told as an intern that she can't say anything about this, and she learned that the high ups at this hospital were buddies with the high ups at Michigan Department of Health. So it was just corruption, just like legit, straight up corruption that wasn't announced or dealt with earlier. All right, there's the quick version. Any questions? Yeah, I'm surprised I did that in 20 minutes.